Hello everyone. As you may or may not recall, if you've seen the last video, or perhaps you saw me in person, I'm Donovan. I am a graduate student here in the Boston University Antarctic Research Group, and I am currently working on Antarctic glaciology. So you also will hopefully remember that I am Great Falls High, class of 2012, and I am throughout the year going to be talking to you all about how the things we do here at the BU Antarctic Research Group relate to the things that you're learning in your Earth Science class. And so today we're going to be talking about mapping and geologic mapping and how geologists use geologic maps to infer things about the environment. The talk is called If You Can Taste It, You Can Map It, and we're going to talk about why that's true as we go throughout the talk. Hopefully by now you have seen at some point in your life a topographic map. A topographic map is like a three-dimensional view of a place, but in two dimensions, on a flat surface. So you can see these lines all over the map, and these lines have a very specific meaning. Those lines correspond to an elevation. So if we look closely, you might not be able to see them perfectly on this video, but if we look closely, we can see the numbers that are associated with each line, and that tells us the elevation at that point on the map. So each of the lines also corresponds vertically in time. So it's an elevation, and there's a set distance between those two lines in space. So we have 5,200 feet here, so that's 5,200 feet high, and we have 5,400 feet here, and that's 5,400 feet high. 5,200 feet high, 5,400 feet high. So there's 200 feet in between those lines at all times. So you can imagine there's a 200-foot elevation change between these two lines everywhere on the map. So if we're looking here, where we have two lines really far apart, that means the elevation is changing 200 feet over a really wide area. That means it's probably pretty flat, right? Because if I walked from right here all the way over there, I'd only change 200 feet in elevation. But if I did it over here, where the lines are much closer together, I'd be changing 200 feet over a much smaller space in time. Or I mean, space on the map, in reality. So I'd have 5,200 feet, 5,400 feet, and I'd be doing that over, like, say, half a mile instead of maybe 5 miles over here. That's the basic idea behind a topographic map. These lines are called contour lines. So the lines show us the contours of the Earth's surface. This map is of Glacier National Park. So you can see here we have Lake McDonald. Many of you have probably been up to the park and maybe even been hiking here on some of the trails that are shown on the map. So contour lines are very useful because as a geologist, I can look at this map and I can say, oh, well, I'm seeing a great change in elevation over a short distance here. That means it's probably very steep. Maybe that's the top of a mountain. And I'm seeing a change in elevation over a great distance over here. That's a flat area. So I can imagine, with enough practice, you can imagine the differences in topography. Topography is the shape of the Earth's surface. You can imagine the differences in the topography all across this map. This is a very different map, and the first thing that you can tell is very different are the different colors on the map. And in earlier classes, I asked them, what do they think those colors represent? And we got very different answers. Some people thought it had to do with the weather. Some people thought it had to do with the elevation again. And I'm going to tell you the answer since I can't ask you to tell me. And the answer is that these colors all correspond to different layers of rocks. They correspond to the different geology of the elevation at that point. So here we have a purple rock type. It's labeled somewhere over there. We have green, and they're also correlated along the contours. So if we look right here, this is called a cross-section, and it is like cutting into the surface of the Earth like you would cut into a cake. So you have layers in a cake, right? The surface of the Earth has layers as well. And so those layers correspond to the different geologic units or different rock types that are deposited. So as you go throughout the semester, you're going to learn a lot more about geology, and you're going to understand what all these different rocks mean. But for now, I just need you to trust me when I tell you that there are different layers to the surface. So if we look here, this is cutting into the surface of the Earth. We've cut in, and we're peeling it back so we can look at the different layers. And there's a different rock type, right? We have, what's this? Saya, and this is Pritchard, and a sill right here. So we're looking at those different layers, and those different layers are represented at the map. So if I'm here at Shepherd, at the top of this mountain, I'm in Shepherd rock type. But if I go down the mountain, I'm in snowslip rock type. Well, we can see that, right? We can see the purple at the top of the mountains, and we can see the green as we go downhill. So we're moving horizontally through space. We're moving horizontally down the mountain, but we're also moving through the different rock types. And in a way, we're actually moving back in time, because these rocks here at the bottom were put there first. They were deposited first. So we can look at the surface of the Earth and go back in time just by seeing these different types of rocks. So if you don't believe me that there are different types of rocks in different layers in Glacier National Park, I put a picture on here so you can see it. So we have horizontal, nice flat lines here in this photo, and these correspond exactly like you see up here. So we have different units, different rock types. So as I'm standing here at the top, I'm in one rock type, but then I see this layer here. I walk down the mountain, and I'm in that unit. So I've walked from there to there, purple into the green, purple into the green. So these are very useful maps for us because we can say, oh, well, maybe this rock type corresponds to an ocean. That rock can only be formed in an ocean. And perhaps the rock above it can only be formed on land. So we know that sea level may have changed in between the deposition of those two rocks. So like I said, it's kind of like time traveling, but with rocks. So how do geologists make a geologic map? How do those of us who are interested in geology go about and put those different colors down on paper? We take our handy-dandy field notebooks. We have lots of different tools that we use, and we go to places like this here in the desert in California. This is in the Mojave Desert. This is one of my own photos. And you can see again, we have lines. We have horizontal deposition of rocks. Those lines, again, can correspond to different points in time, and different types of rocks that are deposited correspond to different events in Earth's history. But if we look at this rock type, if we look at these rocks here, we see something very different. They're no longer horizontal. They're straight up and down. And again, I asked a question in the last class. If I told you that we're in Southern California, and I told you that there's some sort of big event that has made these rocks no longer flat, you might guess that it was an earthquake. And a lot of people did. A lot of people guessed it was a good guess. It's an earthquake. And that's exactly right. So here, we're able to look at the rocks and know that there is a fault somewhere nearby. And that's really important because if I live in Southern California, I do not want to build my house on a fault. So I see over here we have some semi-flat. We have maybe 45-degree angle rocks. We have 85 to 90-degree angle rocks over here. And those are very different from the same place where we have flat. So there's faults at work here. This is my field mapping class. This is me as a junior in college. There's me. I'm not wearing my handy field hat, but others are. And this is that area behind me. This is the same field area. These are all the same rocks. And this is the first geologic map that I ever made. So you can imagine me with my rock hammer. We have in this pouch is a little field lens. And we go out and we look at all the different rocks. So we walk around this big basin and we hit the rocks with our hammer and we listen. A clink means something very different than a thunk. And those can give us hints about the rocks that we're looking at. And I take my field lens, my little lens here, and I get up really close and I look at the different types of minerals and I look at the different grains in the rock. And that tells us something else. And the talk is called, if you can taste it, you can map it. Because if you're walking around with a lot of geologists in a place like this, you might see them picking up rocks and putting them in their mouth to taste them. Because certain rocks have a lot of salt in them. And that salt generally will come from a marine environment or an ocean. The ocean's salty. When you have a rock that's deposited, that salt gets included in it. And so we can taste the ocean in a rock that might be 200 million years old. And so we use all of our senses. We use how they feel, we use how they taste, we use how they sound in order to be able to make maps like this and to differentiate between a rock that we would map as blue, one rock type, and a rock that we would map as brown, a different rock type. And you can also see, you might not be able to see it, but you'll have the slides at your disposal so you can look more closely. You can see these lines on the map. So we have a line there, we have a big line down the middle, another line, and those are faults. And so if I'm going to build a house in Rainbow Basin near Barstow, California, I'm not going to put a house on one of these lines. I do not want to put a house on a fault. And that's one of the very important applications of geologic mapping, is to be able to pinpoint places where it might be dangerous to build, it might be dangerous to put a freeway, it might be dangerous to just simply put, a school or something. So we can learn a lot from looking at these geologic maps. Here's another picture. You might imagine if we had a topographic map, this is another place I mapped, we would have very spread out lines here, right? It's very flat, so we'd have lines that are very far apart. The change in elevation is not very great over a short amount of time, or a short amount of space. So we have wide lines there. We have really close together lines here as we go up the mountain. And again, we can see that we have rocks that used to be flat, but are now tilted up. So there's been some sort of event, an earthquake, that has made these mountains form. And this is how we understand so much of the Earth's history. There were faults in Glacier National Park, there were faults in central Montana, and when we look at all of these different areas, we can tell their history. We can see how the surface of the Earth has changed. And that's what we study as geologists. We study that's what I study as a geologist. A smaller field within geology is how the surface of the Earth has changed, and that's called geomorphology, but we'll get to that later. I've got a couple more photos. No, same place, beautiful field area. And I think I'm going to provide Mrs. Thomas, I'm going to provide Mrs. Thomas with a map for you guys to look at. And so you'll have a couple of geologic maps of the Great Falls area. And with that, I am going to introduce one of my colleagues. He is a geologist, geophysicist here in our group. His name is Sean. And he's going to talk to you more about what it's like to map on the surface of Mars.
All right, hey guys. Thanks for that intro, Donovan. Appreciate it. Yeah, like Donovan said, I'm a postdoc in this lab. And I'm going to talk to you guys a little about something almost completely different. We're going to go off the surface of the Earth, keep on going until we land on Mars, and talk about how we apply some of the techniques that he was just talking about, but a different suite of techniques to help us map and understand Mars. And the main things we're going to try to understand, we're going to understand the history of Mars, and the most important thing right now is trying to follow the water, as NASA says, and understand where we might be able to find water on Mars. So I kind of want to take you through this a little bit. And I'm not sure how much everybody is innately familiar with Mars, but it obviously has a lot less gravity than Earth. It gets a lot less sunlight and is further away from Earth to the sun, and therefore that's going to impart quite a lot of differences. The main one being it's quite a bit colder. So we're talking minus 120 degrees or so at the Martian poles. Around the equator, maybe minus 50 degrees Celsius, which is still pretty cold, and also extraordinarily dry. So almost zero precipitation a year. And if you think about the Earth, obviously that's a lot colder and drier, but there's one special place on Earth that's actually very similar. And that's where I put in this little yellow box. And that I'm going to talk quite a bit more about in a minute, but it's called the McMurdo Dry Valleys, the Antarctic Dry Valleys down in Antarctica. And if you'll notice the temperature differences here, we've got very similar temperature, about minus mid-50s at least in a certain region of Antarctica, as we do in Mars. And also, we also have extraordinarily low, for Earth anyway, precipitation. So we've set up an analogous space where we can go and study and physically touch and tell us something about Mars. But what if we can't go there and physically study it? Because that's only one way. The other way that we know about Mars Oh, and before I go there, I just want to tell you, these are two different images, that the Martian surface, and then down here we have the dry valleys of Antarctica. And you can just visually see there's a lot of similarities, and I'll go over some of these in just a little bit more. But if we can't physically go to Mars yet and pick up rocks and look at things with our own hands, we have to rely on obviously remote sensing. In this case, I'm talking about satellites, and a lot of satellites and a lot of probes which have flown to Mars. These guys in the middle have actually landed on the surface of Mars, and they've given us a lot of information. And then everything orbiting around just represent different probes that we've sent at one point in time to look at Mars in a little bit closer the way that we can't do on Earth. So let's talk about Mars a little bit before I get into the details. You can already see a lot of topography. And one thing to think about when I talk about Mars is that Mars, so Earth wobbles on its axis at about 23 degrees now, right? 23.5 degrees. But Mars can oscillate anywhere from about 10 degrees to about 35 degrees on its axis when it rotates around the sun. And that does some interesting things when we start talking about where we might be able to go to find water on Mars, or in this case, it's going to be ice, because remember how cold it is. And that simply means that depending on if its tilt or its obliquity is closer to 45 degrees, it's going to accumulate kind of in this central equatorial range. If it's a little bit less, at around 35, it's going to be up here, this area we call the dichotomy boundary, and I'll show you some more images in that in just a minute. And if it's relatively straight up and down, by relative I mean still 30 degrees, it's going to accumulate up in these mid-latitudes. So kind of keep that in mind. And that also is going to overlay on the other thing, which we've already talked about some today. Donovan talked a lot about topographic maps and digital elevation models. And this I just want to show you is the rough elevation or a digital elevation, a topographic map of Mars. In this case, color up here represents elevation above some mean datum, as we would say, some 0 point. And the thing to point out and to keep in mind is, the tallest mountain on Mars, Olympus Mons, or one of these tall mountains over here, Tharsis Mons regions, we're talking almost 60,000 feet, so 3 times as high as Mount Everest, so significantly taller mountains. This is not a barren landscape. It's got a huge amount of topography, huge amount of mountains, canyons, scarps. It's a really incredible topography. And that's one of the things we want to understand, is what that topography can tell us. So keep in mind the elevation differences on Mars. You can see all the craters as well, something else to point out, along with that wobbling of the Martian tilt axis around the sun, and when we start talking about what kind of features we're going to map. So these are the two things to think in mind in broad terms. And then this is just a plot of all this shows right here. You'll notice that on each of these 3 panels you see a series of dots, and that's overlaid on the background. The background is just the Martian surface. It's kind of hard to tell with this resolution, but it's essentially this map. And we've got a series of dots. And each of these locations are where that we have laboriously looked at satellite imagery or probe imagery, and in some cases surface imagery, and identified certain types of landforms that we can then that will then help us tell us something about the surface. So let's talk about the first panel first. We call it desiccated terrain. That's one terminology for it. We can also talk about it. Another phrase I'll use is polygonized terrain or patterned ground. And if we go and we look at what that actually looks like on the surface, here we have that map again, and this is the type of image we're looking at. This is about, I don't know, 4 kilometers by 4 kilometers. And this resolution is tricky to tell, but essentially Mars, a bunch of the surface, you'll see this almost regular pattern on the surface of this polygonized or patterned ground. And I talked about Antarctica a little bit, and the reason is because we're able to see that exact same setup in Antarctica over here. You can see also very similar pop-marked features. In this case, it's almost a hexagonal pattern. And we know from going to Antarctica that what this represents, at least in this case, is a thick layer of ice underneath the surface, which is slowly cracked from thermal expansion and allowed us to pick up this signature. And that model is just right here. You've got an ice layer underneath, and then the brown represents dirt on top. And then that pattern forms as it contracts and changes. And if you want to see what that looks like on the surface, and one thing that's important about that is it helps us know where the ice may have been, because we can see desiccated terrain in certain latitudinal bands. You'll notice that they're regular here. And it shows us something about where the ice was and then how it eventually went away. And this is what it might actually look like if you're standing on the surface of Mars right now. In this case, we're not. This is one of our study regions in Antarctica, but this is what it might look like. And just to give you an idea of the scale, way down here are some little itty bitty people. And then just to prove the point, somewhere around in here, may not have been exactly there, but if you were to dig down, you would see this massive buried ice. So there is ice there, and if we can correlate what we see on Earth with where we find ice at a similar environmental condition, and we go to Mars, we have a pretty good understanding that we're going to find the same thing there. So it's pretty exciting. So what was one of the other things I was talking about? In this case, the generic term is VFF, or viscous flow features. It's kind of some big words that really all that means is we're talking about essentially buried glaciers or flowing rock glaciers, some type of ice that's flow, and it's usually mixed with dirt and sediment. And this is a great example of one that was found on Mars, and this is coming down from a crater wall and flowing into the base of this actual crater. And we can again take what we know about Antarctica and see very similar features. Here we have almost the exact same scale, and you can see this big flowing lobe, and we know that this is a glacier underneath a thin veneer, relatively thin veneer, a meter or so of rock and dirt. We're going to call this a buried glacier. Another great example of where we're pretty positive we have existing massive ice underneath. And if you were to, again, go to the surface and look at it of Mars, this might be what you're looking at. Here we see these big flowing features that are brown. They look like dirt, but it's actually massive buried glaciers underneath there. But just one thing to say before I let you guys go is that everything I've talked about really applies to the Martian surface as it is today as far as finding existing buried water ice. We're talking in the past maybe 2.5 billion years to present. And if you go back even further in Martian history, there's all kinds of surface features I haven't had a chance to talk about which have been able to map out, which let us know that at some point in Martian history there's a high probability there was actually flowing water, maybe even lakes, maybe even something we would consider an ocean of liquid water, which is pretty exciting. That's all I have for you guys. Thank you so much. I just want to give you an idea of the type of, quote, mapping that we do on Mars and how we use different tools to do it. So thanks so much. Appreciate it.